So now that we took a look at the results of the models in terms of their AUC, um, we said that choosing a model generally is determined by how good they perform on the validation dataset. Now, one consideration to have is the models that are runner apps. Do they perform similarly or are they completely different? So one thing to consider is the complexity, just as I mentioned. In this case, we have only 10 degrees of freedom, and honestly, in these three models, the three of them perform so similar that any one of them actually could essentially be performing the same on the validation data set. So in this case, it would be okay to not necessarily choose model number three because it performs slightly better, but you can choose any one of the models. Um, so let's for a second think that let's choose model number two because it is easier. Um, it's less complex and easy to interpret. So remember, the more degrees of freedom you have, the more interpretations you have to make in terms of relationships between the variables and the response and things like that. So let me show you the summary of Model 2. And again, we named it step dot M2. So we have these are the predictors. It is easy for us to make direct interpretations between these predictor variables and the response. Um, and we have a strong performing model compared to the rest. So having done that, the next thing that we want to do is basically choose what cutoff for the propensities is going to work best for us. Um, so next step would be to determine the optimal cutoff. And for a second, let's assume that one of the classes, I mean, the prediction errors are basically the same. So if we assume that, then we can use the courts function from the caret package. So we can go ahead and call the caret package and use the courts function. And just to remind you how it works, we have to basically let the courts function know the results from the ROC function, and we saved it in those objects named r1.train, r1.valid. We want to use the validation results. So this model 2, which is the model we're going to use, has r2.valid as the object that contains the cutoffs, and we want to select the best cutoff according to the threshold. So that is using threshold. So that's going to give us the best cutoff of that model, the best propensity cutoff, 48. So what that would do is anything above 0.48 is going to be classified as a yes, and anything below or equal 0.48 is going to be classified as a no. That is, so let's put it together so we can look at this. We can say, we can put the actuals and the predicted values in a data frame. Let's do validation target B, that's the actual, and the propensities, we can put those, and we named those as PM2, that is the validation one. So we have P model 2, and those are my propensities for model 2. So if we want to print some observations here, let's print a few more. We have the propensity scores and the actuals. Now remember, this is the cutoff that we selected, so anything above that is going to be classified as a yes. So this observation is going to be predicted as a no, as a no. This actually is as a no, and we can see that we're going to make some errors. So all of these are going to be classified as a no. This observation is going to be classified as a yes, and so is this one. So we want to see how good this model is, and we want to see the accuracy, we want to see the specificity, sensitivity. So let's put the predictions here in let's use the as factor function, and we're going to use the if else. And we're going to say if p dot m2, which is that probabilities, is greater than that cutoff, let's say 0.4812, then we want to classify this as a yes. Else we want to classify this as a no. And this is this if statement is put under the as factor so that it contains the right levels. So let me show you, let me print this so you can see some of the values here. And again, the idea would be to put it in this matrix here. So let's you can also append it to this matrix so that you can have it there. So either way it's fine. So one thing we can do is put the confusion matrix. So let's do confusion matrix, and again, whenever you type in the function, you can see that this comes from the caret package. So confusion matrix, and we want to put the predictions, that is the predictions that we have. You can do the next thing is the target variable. We'll do it this way and put a positive class is equal to yes. And let me install the package required here just to make it work. And we can see that the confusion matrix here, we have a sensitivity of 61%, we have an accuracy of 58%, specificity of 55.1. Again, there's a couple of things that you need to be careful on. The first thing is that this data set is oversampled, like I mentioned before. So we would need to adjust these values to get what sensitivity and the specificity and the accuracy for the adjusted values. We would have to get it. So just think of it this way. This is probably not going to be the accuracy of the model when you implement it, but it's going to be dependent on the actual proportions of the yeses and nos. This is how we would, the steps that we would do when we wanted to basically get the predictions and the performance of the models using a different cutoff.